By the end of this lesson, you should be able to define the momentum of an object. Define momentum, P, as the product of mass, m, and velocity, v. That is, P equals mv. State the principle of conservation of momentum. Compare the velocity and the time it takes for the lorry and the car to stop. Which is harder to stop? From the same initial velocity, the lorry takes a longer time to brake, hence it is harder to stop than the car. It is much easier to stop the same lorry if it is moving with a low velocity. Why? Both balls are moving with the same velocity. Why do you think the bowling ball was able to knock down the bowling pins, but the plastic bowling ball could not? The bowling ball has a bigger mass. Let us look at the next video. Both balls have the same mass. Why do you think one of the bowling balls was able to knock down all the bowling pins, but the other similar balls could not? It was moving faster or with a higher velocity. What can you infer from these observations? We can conclude that both velocity and mass of the balls affect the number of pins that fall. In effect, the product of the mass and velocity of an object is called the momentum of the object. The SI unit of momentum is kilogram-meter per second, as the unit for mass is kilogram and velocity is meter per second. It is a vector quantity. It has both magnitude and direction. We see from the definition, momentum of an object depends on mass and velocity. Hence, a moving object can have a large momentum if its mass or its velocity or both are large. For each of the following situations, observe and then identify which of the bodies have a larger momentum. What happens to the balloon when the air rushes out? the balloon moves in the opposite direction. What happens to the skateboard when the boy jumps off? The skateboard moves in the opposite direction. What can you say about the momentum of the rifle and bullet before the bullet is fired? Why? The momentum of both the rifle and bullet is zero because they are at rest. What can you say about the direction of the bullet and the rifle after the bullet is fired? The rifle moves in the opposite direction to the bullet. Compare the velocity of the rifle and the bullet. The rifle moves with a much smaller velocity than the velocity of the bullet. Why do you think that is so? Because the mass of the rifle is bigger than the mass of the bullet. Do you think the momentum of the bullet and rifle are equal? The momentum of the bullet and rifle are equal in magnitude, but opposite in direction. So, what can you say about the momentum of each of the rifle and the bullet after the bullet is fired? The momentum of the rifle is the same as the momentum of the speeding bullet, but they are in opposite directions. So, what can you say about the total momentum of the rifle and bullet after the bullet is fired? The total momentum is 0. Total momentum of rifle and bullet before the bullet is fired equals to total momentum of rifle and bullet after the bullet is fired. In other words, no momentum is gained and no momentum is lost. We say that momentum is conserved. For an isolated or closed system, total momentum is always conserved. We call this the principle of conservation of momentum. The moving balloon, the boy and skateboard, and the rifle and bullet are all examples of explosion. In explosions, momentum is always conserved. The video shows a collision between two balls of equal mass. Describe the motion of the balls before and after collision. Only the white ball moves before the collision. After the collision, only the blue ball moves. We know that momentum is always conserved. What can you say about the velocity of the blue ball after the collision? The velocity of the blue ball after collision is the same as the velocity of the white ball before collision. For an isolated or closed system, total momentum is always conserved. We call this the principle of conservation of momentum. Two objects of equal mass approach each other with equal speeds. Describe the motion of the objects after the collision. What can you say about their speeds? They bounce off with equal speeds in the opposite direction. This is an example of an elastic collision. Let us look at another collision. Describe the motion of the objects after the collision. What can you say about their speeds? They bounce off with much lower speeds in the opposite direction. This is an example of an inelastic collision. Let us look at another video. Describe the motion of the objects after the collision. What can you say about their speeds? They stick together and come to a complete stop. This is also an example of an inelastic collision. The total momentum of those systems is always conserved.
We are going to find out whether momentum is conserved in a collision. Click the play button and observe the animation. Can you describe the total momentum of the system in the collision between the cart and the dropped brick? The total momentum of the system is conserved. Before the collision, the momentum of the cart is 120 kilograms centimeter per second, and the momentum of the dropped brick is 0 kilograms centimeter per second. The total momentum of the system is 120 kilograms centimeter per second. After the collision, the momentum of the cart is 60 kilograms centimeter per second, and the momentum of the dropped brick is 60 kilograms centimeter per second. The total momentum of the system is 120 kilograms centimeter per second. Now let's change the mass of the cart and see what happens to the total momentum of the system. Complete the table. Consider 5 marbles of equal mass, which are hung at the same level above the ground. This device is popularly known as Newton's cradle. Observe the animation. Drag the marbles to start the animation. Can you predict the number of moving marbles before and after collision? Yes, the number is equal. What can you say about the speed of the moving marbles before and after collision, and why? The speed is the same because the mass of the marbles is the same. We can now fill in Table 1 to record your observation. how can we apply the conservation of momentum to explain the situation? As the total momentum before and after a collision is conserved in an isolated system, the number of moving marbles before and after collision must be the same as they have the same mass. Dad whizzes around the skating rink and suddenly notices Ahmad standing directly in his path. To avoid knocking Ahmad over, Dad picks him up and continues moving. Find the velocity of Dad and Ahmad after Dad picks up Ahmad. Fill in your answers in the table. Which specific law did you apply to arrive at your answer? Yes, the law of conservation of momentum.